Hello, ladies and gentlemen. We're going to do 9.7b today. We're going to be doing a little bit more work with our Taylor and Maclaurin polynomials. At the very end of our video, we are going to do an example on the Lagrange remainder or the remainder of the Taylor polynomial, and then we will eventually do a little bit more work with that, potentially on a C video. So let's just kind of jump right back in with an example of yesterday's work. So let's find the third Taylor polynomial for f of x is equal to the sine of x, and then we're going to expand about c is equal to pi over 6. So let's go ahead and work through this example, and then I have another example for us, and then we'll start talking about the remainder. Alrighty, so if we just jump right in, f of x is equal to the sine of x, then I'm going to evaluate f of x at pi over 6, and I'm going to get a half. And I'm assuming you're brilliant and you remember all of our trig. Then I'm going to do the first derivative, and I'm going to get the cosine of x, and I'm going to evaluate the first derivative at pi over 6, and I'm going to get radical 3 over 2. And then I'm going to do the second derivative, and I'm going to get a negative sine of x, and then I'm going to evaluate the second derivative at pi over 6, and I'm going to get a negative 1/2. And at this point, I'm not showing my work for this because I assume this is old information. And then the third derivative is going to be a negative cosine of x. And then the third derivative, evaluated at pi over 6, is a negative radical 3 over 2. So now I have enough information, I can write my Taylor polynomial. So the third degree Taylor polynomial is going to be f of pi over 6 plus, and then I'm going to have f prime of pi over 6 times x minus pi over 6. And then I'm going to have the second derivative evaluated at pi over 6 times x minus pi over 6 quantity squared over 2 factorial. And then the third one is the third derivative at pi over 6, x minus pi over 6 to the third over 3 factorial. Well, we have all these values, so I'm just going to go ahead and substitute everything in. So the third degree Taylor polynomial is going to be, here's a half, and then I'm going to have radical 3 over 2 times x minus pi over 6, and then I'm going to have 1 over 2 times 2 factorial times x minus pi over 6 to the second, and then I'm going to have minus radical 3 over 2 times 3 factorial times x minus pi over 6 to the third. Phew! Alrighty, so that wasn't too horrible. Okay, so let's go ahead and start our next example. We're going to come back and use this information later, so don't let it wander too far away. So for the next example, I want to use a fourth Maclaurin. And remember that a Maclaurin, I keep wanting to put a G at the end of that, which is really weird. For the Maclaurin polynomial, that just means that our C is equal to 0. So it's a Taylor polynomial with a C of 0. So I want to use a fourth Maclaurin polynomial to approximate, and this is going to be a key word that we're going to talk about in just a little bit, the value of the natural log of 1.1. Okay, so before we actually start doing our work, it's important to notice that 1.1 is closer to 1 than it is to 0. Okay, so since 1.1 is closer to 1 than it is 0, we're going to write our function g of x. Did I give you the function? No. Okay, so g of x is going to equal the natural log of x plus 1. So since I can let my x equal 0, but what I want to do is get closer to 1.1, so I'm just going to add 1. So then I'm going to start the process that we did on all of our other examples. So I'm going to say g of x is the natural log of x plus 1, and then I'm going to evaluate g at 0, which is why we call it a Maclaurin polynomial instead of a Taylor polynomial. Well, the natural log of 1 is 0. Okay? My first derivative is going to be 1 over x plus 1, which is x plus 1 to the negative 1, which makes the subsequent derivatives easier. And then if I evaluate that one at 0, I'm going to get still the same thing. It's going to be 1 over 1, which is 1. Alrighty, let me turn the page. So now let's do our second derivative, and then I'll have to go to another page. So the second derivative, and I'm just going to write these down for you instead of doing all of the math because I think you're brilliant, and just in the interest of time. Okay, so then when I evaluate at 0, I'm going to get a negative 1. Alright, so hopefully you'll keep that handy and let me go to another page. Okay, so we're up to the third derivative, and that's going to be 2 over x plus 1 to the third. And remember, oops, you can't see it. Remember, when you evaluate these, it's easier if you make this a negative exponent and bring it up to the top when you're calculating your derivatives. So I just am writing this because I think it's easier when we substitute our values in. And then when I do the third evaluated at 0, I get 2. And then the last one, the fourth derivative, is going to equal a negative 6 over x plus 1 to the fourth. And then my fourth derivative evaluated at 0 is a negative 6. So now I'm ready to write my fourth degree polynomial, and it's going to be g of 0 and then plus g prime of 0 times x plus g double prime of 0 times x squared over 2 factorial plus g triple prime of 0 x cubed over 3 factorial. And then the last guy is the fourth derivative evaluated at 0, x to the fourth over 4 factorial. Well, because we've already found all these values, we can substitute everything in. This little guy goes to 0. So when I rewrite my fourth degree polynomial, it's going to be x minus 1 over 2 factorial times x squared plus 2 over 3 factorial x cubed minus 6 over 4 factorial x to the fourth. All right. And so if you'll remember, when we started this, we're actually trying to approximate the value of the natural log of 1.1. So that's where I'm going to go back now to the approximation. So I have the natural log of 1.1, and that's going to equal the natural log of 1 plus 0.1. And this is approximately equal to our fourth degree polynomial evaluated at 0.1. And then we would take this and substitute it into our original equation, and this would become 0.095303. So I have a couple of general thoughts that I want to record. So I have some thoughts that we want to record about this process of approximation. So the first one is, and the thoughts, are about the accuracy of the Taylor or Maclaurin polynomial. Sorry, I was just looking at the time to make sure I hadn't miscalculated my time for use in approximations. So these are going to be what our generic thoughts are about. So I guess this little guy's going to have to move down a bit. So the first general thought is that the approximation is better or more accurate at x values that are close to C, because the further I get away, I guess I should write some semi-decent grammar, the further I get away from C, the less accurate my approximation becomes. And then number two, the approximation, and then we're going to say is better, and it's typically or usually is better for higher degree Taylor or Maclaurin polynomials. Whew, that's a lot of writing. Than for those of lower degree. So we'll just scribble that out. So the higher the degree, the better the approximation works. Alrighty, so if I have a lower degree, it really doesn't do me much good. Alrighty, so what I want to talk about now is when I use a Taylor polynomial or a Maclaurin polynomial to approximate a function, it's important to know what the remainder is, and sometimes we call this an error, and I'll give it a specific title in just a minute, so what it might be. And I think I have, let me take a sneak peek at my notes later because I rewrote it, and so I'm going to kind of skip around on my notes a little bit just because of the way our book is organized. So a function is equal to its polynomial approximation plus a remainder, okay? And so this remainder is what we're interested in talking about now. And so just to clarify a little bit, I'm going to go back and show you the calculation. The book example is a little bit tedious, and I pulled in a couple of other resources, and it's also a little bit tedious. So my guess is we will spend a couple of days talking about this remainder for our approximations. Alrighty, so as we try to calculate this remainder or the accuracy of our polynomial, and we're using our polynomial to approximate a specific value, it becomes important to find this remainder, but sometimes I can't actually find the remainder, and so I actually end up doing a process, and I'm looking for an error boundary or bound. Okay, so I'm looking for an error bound. Well, I have a handy dandy little formula, and it's called the Lagrange, L-A-G-R-A-N, Lagrange Error bound. And I'm going to give you, I'm kind of taking my notes a little bit out of order, but so if I have Rn x, this is going to equal, and I'm just going to have you write it down for right now, and then we'll talk about its individual pieces and then where it fits in what we've been doing. N plus 1 factorial. Alrighty, so if I take a function and then I come up with the Taylor or the Maclaurin polynomial to approximate my function evaluated at a specific point, then I'm going to have a little bit of error. And the Lagrange error is a way of calculating what that potential error could be. Alrighty, so if I have a value, and so let's say I've chosen, how do I want to write this? So I have chosen Z. Well, Z is going to be in between my X value, so the C and the X. Okay, so this is going to be a value that's in between the value that we're approximating it at and the actual value for the function. And I know this seems really creepy right now, but we're just kind of trying to set the stage and trying to potentially come up with how much error do I have when I make a polynomial approximation of a function. Alrighty, so if I go to my next page, if I went back to my polynomial, and let's say I had f of x is equal to f of c, and then I had f prime of c times x minus c plus f double prime of c, x minus c quantity squared over 2 factorial. Well, these are our polynomial approximations. This is either a Taylor or a Maclaurin. So then it's going to keep going until I get f of n times c times x minus c raised to the n. Sorry, that's not times c, that's f to the degree of c, and then over n factorial plus the remainder. Okay, and so then I'm going to have, this is my remainder, alrighty, and then that particular formula, and I'm going to kind of draw a line through it, is going to be the function to a degree, okay, so it's going to be n plus 1, times z, which is that value in between that we're going to try to manage to approximate our error over n plus 1 factorial. So this is just a process, and so this is where I think it gets a little bit creepy. So sometimes I actually can't come up with a really specific value for this. So I'm going to say that it's a bound, okay, so I'm going to write it like this. Our n of x is going to be less than a maximum absolute value of a polynomial. There's the degree times some value in the interval times x minus c raised to the n plus 1 over n plus 1 factorial. So it really looks very similar to what we have done in the past. This little guy is what we're going to use to talk about our remainder. Alrighty, I have an example. I don't know that it's going to make the mud any clearer, but we are going to walk through it, and then we will probably spend some more time talking about this on a third day. All right, so let's just attempt to walk through this example. So it says the third Maclaurin polynomial. Remember, a Maclaurin polynomial is a Taylor polynomial where c is equal to 0 for, oops, that's a 4, the sine of x is, and we did this math earlier, so we're going to bring it back in, and then this was x cubed over 3 factorial. So we want to use Taylor's theorem to approximate the sine of 0.1, and we're going to use our third degree polynomial to do that. And here's the kicker, and we want to determine, that's an E, sorry, my handwriting seems to be rather atrocious this afternoon, the accuracy of the approximation. Alrighty, so this is the third degree Maclaurin polynomial that we're going to use to approximate the sine of 0.1. The new piece of information is that we want to determine the accuracy of the approximation. So if we start by using our Taylor's theorem, we know that the sine of x is approximately equal to x minus x cubed over 3 factorial plus the remainder, or our percentage, sorry, it's not a percentage, or our error, okay? So then this is going to equal, here's the x minus x to the third over 3 factorial, and this is where I need to add in the Lagrange error. So this is going to be f to the fourth, evaluated at z, x to the fourth over 4 factorial. And so this is what I'm talking about. We're going to, a Maclaurin says that my x value is 0. I want to evaluate it at 0.1. So somewhere in that interval, I'm going to have my z value, and it's going to be between 0 and 0.1. Alrighty, so then I'm going to approximate the sine of 0.1. So I'm going to substitute these values into here. I'm not going to manage the remainder at this point. So I'm going to get 0.1 minus 0.1 to the third over 3 factorial. So remember, I am neglecting the remainder at this point. And this is approximately equal to this lovely decimal, 833. Okay? So now I'm going to calculate the remainder. So the F4 of Z is technically going to equal the sine of Z. And then I'm going to, and this is where I think the math gets a little bit weird. Okay? This is going to be bounded. Alrighty. So I'm trying to, I may not be able to accurately determine the remainder or the error, and so it's going to be approximately the absolute value. So what I can show is that 0 is less than the R3 evaluated at 0.1, and this is the sine of Z over 4 factorial times 0.1 to the fourth. Okay, and so this is the remainder right here. Okay, if we do this math, we know that this is going to be less than, so I'm not managing this part, the 0.0001 divided by 4 factorial, and this is approximately equal to 0.12345 zeros and a 4. Okay. So now we're just going to make a series of statements. Okay, so the first one is that 0.099833 is less than the sine of 0.1. So this was our third degree Maclaurin polynomial estimation. Okay, so that's what we're saying here, that the estimation, the third degree Maclaurin polynomial estimation is less than the actual value. So now I need to go to a new sheet of paper. So the next statement is that I'm going to write is that approximation 0.099833 plus the remainder or the error is going to be less than the 0.099833. That's a lot of decimals, plus the 0.12345. Okay? And so then we can say, so this was that value that we found when we ran it through our remainder calculation. So this is the approximation. So we're going to write our concluding statement, 0.099833. And remember, this is the value that we got from our third degree approximation, okay, is going to be less than the actual value of the sine of 0.1, which is potentially less than, if I add these numbers together here, and this is my remainder, then the 0.099837. So that shows me that this is the range of values. This is the estimation using the Maclaurin polynomial. This would be the actual value. And then this is the remainder or the error or the Lagrange, I'm not exactly sure how they say it, the Lagrange error. And so that means that the actual value of the sine of 0.1 is somewhere in this interval. Alrighty, that's it for today. We will attempt to do some problems in class today and then probably have to have a little bit more work. See you soon.